afternoon. Welcome to the CERIAS seminar for March 9th. Today I'm pleased to welcome Professor Ryan Henry, who comes to us from downstate. He's a professor in computer science at Indiana University. Professor Henry got his PhD at the University of Waterloo, so he also comes to us from north of here, and is going to be talking to us today about practical private information retrieval.
Thanks. Okay, so as Chris mentioned, I'm going to be talking about private information retrieval. I saw on the website for CERIAS that students are offered credit to attend this, so I was counting on several students, and I kind of tailored the talk a little bit to be more, to teach you a little bit about how PIR works rather than to focus on like the really technical new contributions. So there will be a lot of giving you the background behind how these things actually work, and then I'll talk about some of the new stuff towards the end. So let's start with the problem statement. What are we trying to do? So private information retrieval, as you can probably imagine, has something to do with information retrieval, which is this basic problem of a user trying to fetch some sort of data from a database. So the user is going to issue a request and is going to get back a response. And this in and of itself, there's a lot of interesting research questions that you can ask. What we're interested in is, what if we want some notion of privacy here? So I had a conversation recently with my 10-year-old niece, who was once a very big Justin Bieber fan. And she has informed me that it is no longer cool to be a Justin Bieber fan. So for the sake of this example, let's suppose that this request here is for Justin Bieber videos, which might be rather embarrassing. So we want to figure out, can we protect the privacy of this user who's looking for Justin Bieber videos on the internet? Now, those of you who know about Tor might say, this is an easy problem to solve. You just connect over the Tor network, you send your request for Bieber videos through Tor, you get your response back, and now the website, or the server has no idea who it was looking for these embarrassing Bieber videos. And this, of course, works for this particular example. But what if, instead of searching for Justin Bieber, the user was searching for some top secret patent idea, trying to decide, is this a novel idea? Should I devote the next 6 months of my life to researching this what I believe to be a novel idea? What if the website, or the database that's being queried here, is owned by some multinational corporation with billion-dollar research budget, who sees this idea and goes, that's a brilliant idea, let's bring this to market before that user has an opportunity to commercialize. So here, Tor doesn't help. The website or the server doesn't know whose idea this is, but they still learn the brilliant idea. And so we're solving the wrong problem using Tor here. What we really want to solve is the problem of allowing the user to query the database and having the database not have a clue what it is the user looked for. So we're not going to try to protect the identity of the user. We're going to try to protect the contents of the query. If you want to protect the identity of the user, you can do all of this over Tor, and then you get both notions of privacy. Okay, so that's the basic hand-wavy version of what exactly is PIR. A slightly more formal definition, but by no means the cryptographic definition, is that private information retrieval is just a database technique that is going to allow a user to query a database while protecting from the database server the contents of the user's query. And PIR is how I'll usually refer to private information retrieval. That's the standard acronym. Okay. So some of you might be wondering, is this actually possible to query a database and get responses without the database learning what you asked for or what it sent you? So to convince you this is possible, let's look at the sort of the trivial way to do this. So the trivial way to do this is the user is going to ask the database for something, just a very generic query that says, hey, I'm looking for something. And the database server is going to say, okay, here's everything I've got. Now you can look up locally what particular thing you're looking for. And of course, this gives you perfect privacy because the database server the query didn't contain any information about what you were looking for. The database server just sent you everything. It doesn't know which things you were actually looking for. It doesn't even know whether you found what you wanted. So we get perfect privacy, but the communication overhead is huge. Imagine searching Google this way. You go to Google and they say, hey, I'm looking for a website. And they say, okay, here's the whole internet. Find the website. It doesn't scale very well. So we need something a little bit more practical than this. So there's a second requirement beyond the privacy requirement, which we usually call non-triviality, which says that the cost of this entire interaction between the client and the server should scale as little o n, where n is the number of bits in the database. And in practice, we don't want this asymptotic notion. We really want that the cost of everything is really, really small compared to the time it would take to just download this whole database. So now it's less clear if this is actually possible, but it turns out it is, and there's three basic ways that we know how to solve this problem. So the first one uses homomorphic encryption. This has got some really nice properties, but is extremely slow. Second one uses trusted hardware, which has some promise as long as you can trust the hardware. And the third one uses coding theory, and this is the approach we're going to talk about in this talk, is this coding theory-based approach. Okay, so start with a little bit of formal model. How are we actually going to set this up? We're going to think of our database as a matrix. This is an R by S matrix over a finite field. If you're not familiar with finite fields, all you really need to know here is that it's a mathematical object where you can do addition, you can do multiplication, and you can find inverses. So you can find something. If I give you A, you can find A inverse. So when you multiply them together, you get 1. And as long as we just need any sort of setting where we're working in a finite set and we have those properties. Each of the rows of this matrix is one of the records in our database. So these are the things that a user might try to fetch, or the rows of this database. And we've just decomposed each record into a sequence of words, of elements from this field using some sort of encoding mechanism. Now to query this database, well, this is the non-private way to query this database. Perhaps not the way you would do it if you were implementing non-private queries, but this works. So you could send a standard basis vector. So one of these vectors from the most obvious basis for the vector space, f to the r. So r is the number of rows in the matrix. So there's just a vector that has all zeros everywhere except for one position that has a 1. So if you're looking for the jth row or the jth record in this database, you're going to put the 1 in the jth position of this vector. And the database server in this non-private scheme is going to answer this query by multiplying the vector you sent by the database. And if you do this, it's fairly easy to see that you're going to get the result that you want. So basically, the first row of the matrix is going to be multiplied by 0, and you're going to add that to the second row multiplied by 0, and add that to the third row multiplied by 0, and so on. And only the jth row is going to be multiplied by 1. So all of the other rows are going to disappear, but that jth row is going to be left behind, and you're going to get the record that you were looking for. Okay, so this seems to work, but it's not private at all. So now we need to figure out what are we going to do to take this basic approach and turn this into a private information retrieval protocol. So the idea is to replicate the database, and then this guy here is giving us the second part of the suggestion, and that is we're going to take this query that we were multiplying against the database, and we're going to secret share it using something called Shamir's secret sharing scheme. And this here is Shamir, the one suggesting that. So we replicate the database, and then we secret share this vector component-wise. So we share the first component, the second component, and so on. And we send a different vector of secret shares to each server. Okay, so what is this secret sharing thing I'm talking about? The idea is actually very simple. Suppose you want to share a secret denoted by this purple point with the word secret pointing at it. We want to share this amongst a set of L shareholders so that any pair of them can work together. Then we'll look at the more general case. So in this case, we're looking at any pair of them can reconstruct it. And we want the additional property that any individual shareholder doesn't know anything about the secret. So you could think of this common way to explain why you might want to do this is the generals that hold the keys to launch the nukes, right? You don't want some general who's having a bad day to launch the nukes. But if several generals come together and decide we need to launch these nukes, then we want them to be able to do that. And if one of the generals suffers a heart attack or something like that, we want to make sure that the remaining generals can still launch the nukes. So we want to allow any subset, in this case of 2 generals, to launch the nukes, but we don't want some rogue general launching the nukes. So the way that we accomplish this is we think of the secret as a point on the y-axis, and then we choose a random slope, and we form the line that passes through that secret with the slope that we chose. And then each of the other shareholders, each of the other generals in this case, or each of the PIR servers in our PIR example, are going to get different points on this line. And so, well, as you can see here, the shares are just points on a line. So if one shareholder is trying to figure out what the secret is, you kind of have to ignore all those other points. We just have one point. So it could very well be that this is the secret because the line that passes through this point also passes through the secret. But for any other possible secret, there's exactly one line that connects this shareholder's point to that secret. And so without some other information, it's impossible to tell which of these is the correct secret. So it could be this point, it could be this point, it could be this point, etc. As soon as a second shareholder comes to the table, we now have 2 points, which uniquely determines the line, and we can figure out very easily what the secret is. So this is how you do the 2 out of L version. We want slightly more general version where there's potentially more shareholders required to come together. And so here I'll show the 4 out of L version. The idea is very similar. We let the secret be this point on the y-intercept, but now instead of passing a line through the point, we pass a random polynomial, in this case of degree 3, through the secret, and then we give different points on this polynomial to each of the shareholders. And it's a little bit harder to see how they're going to reconstruct the polynomial from these, but it turns out that it's actually very easy to reconstruct a polynomial through the set of points, and then you learn the secret. So in this case, if 3 points on this polynomial, every secret is possible, but as soon as you have a 4th point, you reconstruct the unique polynomial, and you can just read off what the secret is. Okay, so let's abstract this out into what the scheme actually looks like. So the T out of L, or T plus 1 out of L secret sharing scheme, our goal is we have a secret S. We want to share it amongst L different shareholders. We want to do this in such a way that any T plus 1 or more of them can easily figure out what the secret is, but any T or fewer of them can't learn anything about the secret. And we're going to do this by choosing a polynomial that has degree T. When you evaluate this polynomial at 0, you get the secret, and is otherwise uniform random from our field, with the coefficients from our field. And in order to reconstruct the secret, the shareholders are just going to use, and each shareholder is going to get a point on this polynomial, different point. It doesn't matter which points they get as long as they're not the one that holds the secret. And then to reconstruct, they're going to use Lagrange interpolation or some other polynomial interpolation algorithm. So the exact details of that formula aren't important, but it should be easy to see that asking a computer to do that is no big deal. It can do it very quickly. And this explains why we need a finite field, because we need to be able to, I don't have a pointer. We need to be able to compute that inverse there. So that's basically the only reason we need a field. Okay, so this gives us privacy, but does it actually give us information retrieval? That's the next question. So it turns out it does. The reason that it does is because Shamir secret sharing has a nice property which we call linearity. So the observation here is if you evaluate a polynomial at 0 and you get A, and you evaluate some other polynomial at 0 and you get B, if you add these 2 polynomials together and then evaluate them at 0, you're just going to get A plus B. So they just add up nicely when you add. And if I take the polynomial that evaluates at 0 to A and I multiply it by a scalar C, then I evaluate that. At 0, I get C times A. So I can add these things, and the secrets that they encode just add, and I can multiply by scalars, and the secrets they encode just multiply. Likewise, when we look at what's happening in that PIR protocol, it's all linear as well. So when you multiply a vector times a matrix, you're just taking a bunch of scalar multiples, and then you're adding them together. And when you go to reconstruct the Lagrange interpolation formula, you're doing a bunch of scalar multiplies and an addition. So everything here just requires that scalar multiplication and addition holds. So we can take secret shares, multiply them by scalars, etc. Now we can do our vector matrix multiply. So back to the protocol. The user is going to Shamir secret share this standard basis vector, one component at a time, send the resulting vectors of shares to the various servers. The servers are going to multiply the vectors of shares by the database, send the result back to the client, and then the client is going to use the Lagrange interpolation to reconstruct a vector which gives the row that it was looking for. And this is going to give us perfect privacy, provided not too many of the database servers are talking to one another, and no privacy if that assumption doesn't hold. Excuse me. Okay, so yippee, we have PIR. Can we get on to the new stuff? So everything I've told you so far is been known for a long time, and it's not my own ideas. But what I'm going to tell you now is the new stuff. So the first thing we're going to look at is, can we let users fetch several blocks without just doing several queries in a row? So can we do this at a lower cost? And in particular, we're going to try to let you fetch several blocks and have the cost, all of the various costs involved, be about the same as just fetching one block. So how might we do this? Let's go back to the basic idea. The basic idea was we're going to take one of these standard basis vectors and multiply it by the matrix, but we're going to use secret sharing to split this computation up. If you wanted to fetch several blocks, you could send all of these requests simultaneously as one big long matrix. And now rather than doing a vector matrix multiplication, you're doing a matrix matrix multiplication. And one immediate observation is that the cost of multiplying two matrices, if you use a fast matrix multiplication algorithm, is a little bit lower than the cost of doing each row individually. So we can save a little bit of computation cost, but the communication cost doesn't change, the computation cost doesn't change too dramatically. So can we do better than this? And it turns out, yeah, we can do a lot better than this. The way we're going to do it is we're going to use something called a ramp scheme. So going back to basic secret sharing, we can draw a graph like this to represent how much data, or how much information, not data, is revealed to the shareholders based on how many shares they have. So if we have, this is the 2 out of L version. If you have fewer than 2 shares, I know it's discrete and I've drawn it as if it's continuous, but just ignore that. If you have fewer than 2 shares, you have 0 information, nothing at all about the secret. As soon as you have 2 shares, you jump up to complete information. We know everything there is to know about the secret because we have 2 shares, we can reconstruct the line. In a ramp scheme, we relax this a little bit. If you have fewer than 2 shares, you still have 0 information at all about the secret. But now to get complete information, you have to have, say, in this case 4. You have to have T plus Q shares. So in the secret sharing scheme, it was Q plus 1. Here we're saying, or T plus 1, now we're saying it's T plus Q for some Q, and Q could be bigger than 1. And the upshot of this is we can now fit Q times as many secret bits into each share. So the shares are still just points on a polynomial. They haven't changed. They look exactly like they used to, but they're now encoding Q times as many secret bits. So how might we do this? This is, again, still not a new idea. Ramp schemes have been studied basically as long as secret sharing schemes have been studied. I was an infant when people were first looking at this stuff, so I can't claim credit for this. But this is the way that almost every paper, in fact, every paper that I've ever seen, this is how they do the ramp scheme version of Shamir secret sharing. So in the original version, we had a, say, in this case, a quadratic polynomial. The constant coefficient, I keep thinking I can use a laser pointer, but I can't. The constant coefficient is the secret, and the other coefficients are uniform random. And so the general way to turn this into a ramp scheme, the most common way, is to replace one of these random coefficients with another secret, and then in order to make sure that we still have the level of privacy we had before, add another term. So we increase the degree of the polynomial by 1. We have the 2 lowest order coefficients are now 2 secrets. There's another way you can do it, and this is apparently not very common, but it seems very natural to me. Rather than replacing coefficients with secrets, we can think of, okay, the secret is a point on the polynomial. It's a specific point, and we can encode a different secret at a different point in the polynomial. And again, we're going to have to increase the degree of the polynomial to make sure we get our privacy, but rather than using coefficients to store secrets, we're going to use points. So here we have our first secret at the y-intercept, but now when you evaluate this polynomial at 1, you get a different secret. So rather than the linear coefficient, it's the evaluation at 1 that gives a second secret. And then to form our secret sharing polynomial, we'll choose a couple of other points completely at random, and then we'll interpolate through them to find the polynomial that connects our secrets to these random points, and then we'll evaluate it at some other places to get other shares for other shareholders. So we have 2 different ways to share, in this case, 2 secrets in the same secret sharing polynomial. The question is, why might we want to use one version over the other? And in many cases, it really doesn't matter which one you use, but in our case, the second option has a distinct advantage. So in particular, if you look at the first option, this is a really simple, conceptually, the secrets are just coefficients. You interpolate that polynomial and you read the coefficients off, but it's only kind of sort of homomorphic. So if you multiply two of these polynomials together, that first secret multiplies together. But the secret that you get on the constant, the linear term here, isn't the product of the linear terms of the two polynomials you multiplied together. It's some other more complicated formula. And if you had lots of secrets, it gets more and more complicated. We can tell you exactly what these things are going to look like, but they're never going to be the product of our two secrets. Only the constant term will give us the product of our two secrets, b and d in this case. When we look at the second option, though, right, so the constant terms multiply, the higher order terms do not multiply. When we look at the second option, it's a little bit more complicated, sort of. It's actually not if you look at it the right way. They're both just linear combinations of different bases, so it's actually equivalent. But it's got a nicer homomorphic property. So no matter which point we're talking about, which x-coordinate we're talking about on the polynomials, when you multiply two polynomials together and evaluate it at that point, it's the same as evaluating those two polynomials at that point and then multiplying together. So the secrets when you evaluate at 0 multiply together, and the secrets when you evaluate at 1 multiply together. This is going to be a big advantage for us when we go back to PIR. Okay, so now I said you want to get Q blocks. We have one of these matrices. It's got Q rows in it, and each one is just a standard query. What we're going to do is we're going to use one of these ramp schemes, and we're going to encode all of these queries together in a single vector. So we're going to choose polynomials that pass through. So this polynomial f1 here, when you evaluate it at 0, you get this component. When you evaluate it at 1, you get this. And when you evaluate it at 2, you get the next one. And when you evaluate it at q minus 1, you get this. And then it has t random points added, and we've interpolated through those to get a degree t plus q polynomial, t plus q minus 1 polynomial. And f2, likewise, when you evaluate it at 0, you get this. When you evaluate it at 1, you get this. When you evaluate it at 2, you get this, and so on. So we've taken our matrix with q rows, and we've turned it into still just a vector of secret shares. And then going back to the PIR protocol, we still just send one evaluation of this vector to each of the servers, and they still just do the multiplication. And if you think about it or scribble on a piece of paper, it's very easy to convince yourself that the responses they give back will interpolate to q different records instead of just one. And so if you look at what does this mean for performance, this is giving the per server cost of running the protocol. Goldberg 2007 is the basic protocol that I started with, that I was modifying with the ramp schemes, and then the batch queries is what I just talked about. If you want to get Q records with Goldberg's protocol, you upload a length R vector, but you have to upload Q of them. So you upload QR field elements to each server. You download a length S element for each query. So you download QS field elements from each server. Each server is doing a vector matrix multiply, which takes RS. It's actually 2 RS field operations, not RS. And we have to do that Q times. And the storage cost at each server is RS. They store the whole matrix. In our cost, all of those are the same, but without the Q's around. So we basically, if Q is 1, the costs are the same, but as soon as Q is 2, we've cut the cost down by a factor of 2. If Q is 3, we've cut it down by a factor of 3, and so on. So we have a factor Q improvement in everything except for the storage cost at the servers. So that's pretty cool. But what's the trade-off here? Well, okay, don't worry about the trade-off. Let's just move on. So our second goal is, let's fetch only one block again, but let's do it at a way lower cost than fetching one block used to cost. So the idea here is actually very similar. We're going to take the database in this case rather than the query, and we're going to use these ramp schemes. So first step is you take the database, which has these R rows, and we're going to express it in sort of a block form. We're going to say, let's look at it as R over U matrices stacked on top of each other, where each matrix is of height U. So we're just rewriting at this point. We're saying take the first U rows, call them one matrix, and then they're stacked on top of the next U rows, that's the second matrix, and so on. Then once we've done that, we're going to use this ramp scheme construction. We don't have to choose any random points here. We just interpolate through the various rows of these block matrices. So we find a vector of polynomials where when you evaluate these polynomials, like the first polynomial in this vector of polynomials at 0, you get the first component from you get this guy. And when you evaluate that first polynomial at 1, you get this guy. And when you evaluate the second polynomial in the first vector at 0, you get this guy, and so on. So we're just taking our matrix, we're thinking of it as a collection of smaller matrices, and then we're encoding each matrix into a vector of polynomials. If we want, we could choose some random points in there and we get something called tau independence, which I'm not really going to talk about. It's a useful property if you want to make sure that the database servers can't actually learn the contents of the database they're helping to host. So we're going to assume the database servers are allowed to know that. So here we've taken the database, which was R by S, and we've turned it into R over U by S polynomials. Then we're going to take these polynomials and we're going to give evaluations, these vectors of polynomials, or I guess matrices of polynomials, and we're going to give evaluations to each server. So now each server, rather than holding a database of dimensions R by S, holds a database of dimensions R over U by S. So they're holding a factor U less data than they were before. And the user can query these databases in pretty much the exact same way they were querying before. The only difference is if I want the first row from the original matrix, then I need to query the first row in this matrix, so this row, and I need to hide my secret in the secret sharing polynomial at x equals 0. And if I want the second row, I still query the first row of this matrix, but I hide my secret for this query, the secret standard basis vector, at x equals 1 at a different point. And now when I multiply the two polynomials together, because of that nice homomorphic property I talked about, everything works out and I get back the particular row that I was looking for. So when we look at the cost of this compared to Goldberg's protocol, those Q's shouldn't be there. That's a copy paste there. So we're only looking at the cost to fetch one block, and this should say 1. So this should be RS, RS, RS. In this new protocol, the upload cost is now only R over U because we're sending a shorter vector, because now our matrix that each server holds is a factor U shorter. The computation cost is now R over U by S instead of R by S, so we've saved a factor U computation time at each one of the servers. And the storage cost for each server is also reduced by a factor U, because now instead of holding the whole thing, they're holding something that's a factor U smaller. So we've minimized, again, 3 of the costs by a factor U. I've actually gone through this a lot faster than I had expected. So yeah, there's some more, but I didn't expect to be here quite so soon. So anyways, that's cool too, but seriously, like I just glossed over the trade-off last time. What is the trade-off? There's got to be a trade-off. You can't just like infinitely make things faster. So it turns out, yes, there is a trade-off. And so the trade-off comes from what's called Byzantine robustness. So I kept saying we have L servers, we're going to create secret shares so that at most T out of L servers can collude and we have privacy. If you thought about that, you might have wondered, why would you set T less than like L minus 1, right? You need T plus 1 points to interpolate. You set T equals to L minus 1, and then you can always interpolate, but that way you've maximized the number of servers that are allowed to collude without troubling things happening. And it turns out there's a reason why you might want to set the privacy threshold smaller than the total number of servers, and that's because after we've replicated our database to lots of different servers, we have to worry about what happens if one of these servers is evil or misbehaving in some way, maybe it's a malfunction, and gives us a bad response. Right? So when we're talking to one database server, either that server works or it doesn't. If it doesn't, we're out of luck, right? He holds a database. If he doesn't answer a query, well, we're kind of messed up. But now that we've split it to lots of servers, it only takes one bad apple to possibly spoil the whole query. And so the protocols, in particular the protocol I was just talking about, has a nice way to deal with some of the servers giving bad responses. And that is to look at these secret shares and interpret them as Reed-Solomon codes, for those of you who know what those are, and then you can throw standard coding theory algorithms to figure out which responses were incorrect and still interpolate. But in order to do this, you need to have extra responses. So a nice visualization is, if we're looking at the linear case, you need 2 to reconstruct. If I have extra points on this line, and then one point that's not on the line, it's pretty easy to see that, okay, this was the bad share. I can still figure out what the line is here, because all of these other points are on the line. So the visualization is not so nice when you look at higher degree polynomials, but the basic idea is exactly the same, and there exist efficient algorithms that can figure out which points are the wrong points and can still find the polynomial, as long as we set that privacy threshold to be lower than the total number of servers. Now, in the first paper that came up with this basic protocol, the actual title of the paper was Improving the Robustness of Private Information Retrieval. And the main contribution of this paper was that it could handle this exceptionally large number of Byzantine servers. So L is the total number of servers, T is the privacy threshold, and it can handle this many servers, bad responses, which was a big improvement over prior work. Fast forward 5 years, we have better decoding algorithms and some neat ideas. The bound for this exact same protocol, just changing what the client does, improved to this, which means that now we can handle way more Byzantine servers. So the observation is, if you were happy with T and L and V back here, then there's some wiggle room. We can change the degrees of polynomials, have the same level of robustness, same level of privacy, and maybe use some of that extra space to get better throughput. So we end up with a set of parameters that we can play with. So L here is the number of database servers. T is that privacy threshold. It says how many of them are allowed to collude. So if T collude, nothing bad happens. If T plus 1 collude, bad things. Tau is that independence level I mentioned before. We could add extra random points when we're doing the encoding to stop servers from learning the database. So tau is how many servers are allowed to talk to one another before they can learn the database. By default, it's just 0, but if you want to bump it up, you can. Q is the number of records that we get in each query. U is that parameter where we were shrinking the database down. And then V is how many Byzantine servers we can tolerate. And we can set these parameters any way we want, as long as it satisfies this very simple equation. It's just a linear equation where you're adding them all together. So this gives us lots of wiggle room to set parameters as we please. So I've gone through this way faster than I had actually expected. So I'll say a little bit more that I don't have slides to cover. So one thing that I've actually looked at recently is just how low can we set V? So how high can we set Q and U in particular? I guess the other thing I didn't mention is that you can combine those two approaches. There's a couple of little technical details that are relatively easy to work out, and now I can fetch Q blocks for a factor U lower than the cost of fetching one block, and that's where this equation comes from. Then the question becomes, how low can we set V in practice, right? We want to support robustness for a good reason. How low can we set V? And so if you consider a model where the servers have some reason why they're actually participating, say for example, they get some small monetary incentive to participate. Every time they answer a query, they get a small amount of money for it. The observation is that if they give you a bad response and you're able to reconstruct, so if so few of them gave you a bad response that only V were malicious, only V were Byzantine, and you were able to reconstruct, you not only learn the record you were looking for, but you figure out which ones of these servers gave you bad responses, and you can stop involving them in future queries, and so they stop getting paid for participating. And so if you make a rationality argument based on that, you can show that these servers will actually always behave as if Q and U are both set to the smallest possible value. Because there's a very simple argument to show that they can't tell the difference between, they'll behave as if Q is set to the smallest value, U is fixed. because they can't tell whether Q is being set to 1 or 2 or 3 or 4, etc. And so as long as users occasionally send queries where Q was set to 1 with some, unpredictably with some non-negligible probability, the servers can do this cost-benefit calculation and say, is it worth my effort to try to mess up this query, or should I just answer honestly if I want to keep getting paid? Because they know if they ever get caught, they stop getting paid forever. And then you can make a rationality argument and show, in practice, we can set V to 0 almost always, and then with some probability, you set V to be as high as it can go, and you send a query and you catch any bad guys, and that prevents the bad guys from even trying to mess up queries. So there's a lot of more things that you can do with these techniques. One thing that I've actually been looking at recently with this approach is, so we want to fetch several records from a database. What if we don't know a priori which records we want, but we want to leverage this fact that we can actually fetch Q of them at a time for a lower cost than fetching just one? So there are existing approaches which let you query indexes in a database and figure out what you're looking for, say to search by keyword or to do SQL queries. We can actually combine this idea of encoding the databases together, like shrinking the databases as polynomials and doing batch queries at the homomorphic properties, the additive properties and multiplicative properties of the polynomials, in order to issue queries that go against the database. And the result of the query is a new batch query, a new query for different Q elements that are customized towards what the user is looking for. So you can have index databases that consist of queries. You send a query against the index database, and it creates a new query by combining its rows, and then issues that against a new database and sends the result back to you. And you can actually issue very interesting types of queries. I wish I would have made a slide for that, because it's actually, I just didn't think I'd have time for this. So you can do some really interesting things. So I've been looking at places where this would be a useful thing to be able to do. One application that came to mind immediately is something like Twitter. So if you're querying the Twitter database using PIR, it's going to be really slow because the Twitter database is huge. Not only that, but what are you querying for? Say I'm following Annikit or Chris on Twitter, and I want Annikit's most recent tweets or Chris's most recent tweets. Which row do I ask for? If I know which row to ask for, I've already seen the tweet. So I have this problem of I need to know which row to ask for, and there's a ton of rows because each row is a different tweet, and there's a ton of rows, but there's not that many users. I mean, there are a lot of users, but compared to the number of tweets, there's a very small number of users. So we can use this index idea to say, rather than querying for the row containing Annikit's most recent tweet, I can say I want the row in the index that lists Annikit's most recent tweets. And now I can say I want the 10 most recent tweets, and my query is for Annikit, not for his most recent tweets. And that index database will translate this into a query for Annikit's 10 most recent tweets wherever they happen to reside in the database, process that query against the database, send the result back to me. So now I don't need to know where records reside in the database. I can just say I want to query the most recent tweets index, and I need to know where Annikit's row, which is a static thing in that database, resides, and it'll always give me Annikit's 10 most recent tweets, or Chris's 10 most recent tweets, or anybody else's. There could be other other indexes into the database that let you query it using different views. So you could, for example, ask for the most retweeted queries by Annikit. Or I'm not a big Twitter user, so I don't know other ways that you might want to look for tweets. But anything that you can come up with, you could conceivably build a different index for. And so by querying the index, you're leaking what you're looking for, whether it's most recent or most influential or trending or whatever, but you're not leaking whose tweets you're actually looking for, and you're decoupling the location in the database from how the query is formed. So now the user can issue these queries without actually having to know the whole structure of the database. And in the Twitter example, this is particularly important because Twitter will allow you to query their database, but they actually go out of their way to make sure that you cannot scrape the entire database. They don't want you to know the entire structure of their entire database. They just want you to be able to access it through their API. And this actually lets you do that, whereas traditional PIR techniques wouldn't actually even make that possible. So there's lots of applications beyond just making things faster.
Yeah, so I guess in Twitter case, the most prominent will be hashtags. Uh, one interesting keyword thing can be hashtags.
Right.
Now, coming to here, the batching that you're performing is for the queries from a single user.
Yes.
Can something happen when there are several users who are making simultaneous queries, and maybe you can use some of the batching there?
Yeah, that is a much more difficult problem. There is stuff you can do. So actually, going back to, I said, can we do better than this just using fast matrix multiplication? There's actually a recent paper by, by Ian and Casey. I don't know if you know Casey. Um, where was that? That basically was based on this observation that, okay, is back further than I thought, that multiplying this matrix by the database is a lot more efficient than multiplying each row individually. And so they updated the per C++ as the implementation of this basic protocol, not the stuff I've been talking about today. They updated it so that the server can accumulate a bunch of queries and then do a fast matrix multiplication. So that gives you a little bit of performance gain over processing each individually. If you want to use the ramp scheme-based stuff that I was talking about today, you have to be very careful. So it is possible to encode the queries at sort of random x coordinates within your polynomials so that, and then reveal which x coordinate the query is being encoded into the server so that the server can collect different queries that were encoded at different x coordinates and combine them. But now you have sort of two options from here. So it's going to combine these to build, so just using the additive properties of the polynomials, it's going to combine them to build a single query that it evaluates against the database. Now it can either send that result back to all the users, in which case the users can interpolate to each of these x coordinates and figure out what other people were looking for. Or it can try to randomize things for you.
Yeah,
So
how about
that
users are willing to communicate with each other?
if users are willing to communicate with each other, it's a relatively easy problem. It's actually quite easy to combine them. They can even, if they're willing to coordinate and they're willing to leak to one another what they're searching for, then they can non-interactively send those things that they don't even have to talk to one another as long as they've a priori like agreed on how this is going to work. And then they learn each other's queries. If you're trying to hide from each user the other user's queries, then you either have to trust the database servers to randomize the responses before they send them back, which the randomization is easy, but it has to be coordinated amongst all servers and you have to trust them to do it. Or the users have to somehow construct their queries in such a way that they can decode them, but other users won't know how to decode them. And the only way you can really do that is to issue queries in previous rounds that give you random linear combinations of the database that you can use to hide which standard basis vector you're sending. And you end up in, you have to make some wonky assumptions. You can do it, but the assumptions you have to be very careful about. Yeah, it'd be interesting to see whether there's a really good way to do that, but I haven't put I've thought about it, but not in depth yet.
Well, I have a question. One thing that always has bothered me about private information retrieval is the name. And that is because, it's really, as you say, you're using the terms queries or index lookup, which is really what it is. When we think about information retrieval, it's often best match. There is no exact answer. You're looking for something that's close. Now, and I've always looked at this and said, this just doesn't address that problem at all. I'm wondering, have you thought about this? Because when I realize a lot of what you do, a lot of information retrieval techniques do reduce to matrix multiplications. Have you thought much about, is there a way to get best match retrieval rather than exact match retrieval out of these?
I've thought a little bit about that. And there are some kind of things that you can sort of do. I haven't thought a lot about it, and I'm really not an expert in how the best match algorithms and stuff work, and I agree that there's probably a lot of potential for that. Some of the stuff that I've been looking at is like the index things that I sort of talked about a little bit at the end. I've been looking at how do you look for things where the thing might not be in the database or you don't know where it resides in the database, and you're rather trying to issue queries for like a contextual query. I'm looking for something of this sort, give me the best matches. And so if you can predict what sorts of questions users might ask, it's very easy to prepare indexes that will answer the queries and give the best matches for the query, even if no exact match exists. If you want to be able to do things like find the closest to a particular query when nothing exists and you don't want to have to anticipate all the possible questions, you can do this with interaction. So if there's one query and based on the response you issue another query, then you can build complicated data structures. You can build any data structure really you want and have the PIR query go through the data structure. And then anything that you can solve non-privately with that data structure, you can solve privately. So this is how the keyword searches and stuff typically work. You construct a B tree over the database. The users query the B tree recursively until they found the coordinate that they actually want, and then they issue a query for that coordinate. And so the stuff I've been looking at is explicitly non-interactive. You do not have this back and forth. You send a query, the query gets transformed into the query you actually want, and then it gets evaluated and then sent back to you. But those are really the only two things. And people have done a related sort of SQL query type thing as well that's very similar to the B tree thing I proposed. That's basically all that's been done at this point. I guess somewhat sort of related. I did some work in the past on using PIR to do e-commerce, and we were looking at, so if you were to envision a sort of competitor to Amazon's Kindle store, where everything was purchased using private information retrieval. So we wanted to solve the problem of, can you sell things where things have different prices, and knowing how much a person paid will reveal a lot of information about what it is they bought. So we want to hide the price that they paid, but make sure they pay the correct price. And to throw a wrench into things, let's say there's Amazon Prime memberships. So these people are allowed to get some things for free, and maybe other things are cheaper than for a non-member. And we want to be able to support all of this, but have it completely oblivious. So first off, if you want to do payments, you need to, say, prepay for a credit card or like a debit card type thing that has a balance in it. And now you just have to prove that I have enough money in my thing to pay for whatever it is I'm getting, and I've subtracted the appropriate amount. And we were able to build a nice protocol that lets you do these purchases. Then we started to think, okay, so is Amazon ever going to support something like this? Well, no, obviously not, because Amazon wants to know what you purchased. They don't just want to get the right amount of money, they want to be able to do analytics. They want to know what's purchased when. And so we were able to show how you can build histograms of sales and say, well, this was downloaded X number of times, this was downloaded Y times, and this was downloaded Z times, without revealing who purchased what at what time. And if you have to pay commissions to different people, we were able to show, okay, based on how many times this was downloaded and whether they were Prime members or non-Prime members and so on, how much money is this person who owns the intellectual property, how much do they get paid? And we realized that with that same data, we were able to do things like build sub-databases that, like, you sort the database according to popularity and so on. And you could issue a query against, say, the top half of the database. And so you're revealing explicitly that I don't want something from the bottom half of the database. But the stuff in the bottom half of the database is known to be the stuff that nobody wants. And so most users want stuff in the top half. And so by revealing I want something in the top half, you're revealing I want one of the popular things that everybody wants. And so you're kind of minimizing what's leaked to get the savings of I'm querying a subset of the database. And so using that sort of thing, you could also possibly get some sort of useful information retrieval stuff that we never thought of.
The problem with that one is if I do query the entire database, that's effectively revealing I want something in the bottom half, which is the step nobody else wants, which is exactly what I want to hide what I want. So
that's true. I mean, that was sort of like a passing comment at the end of the paper was, look, you could also do this. There's some intricate privacy ramifications that we're not going to explore. We're just pointing out that this is a possibility and it might be. So if you're doing the half and half thing, we actually assume that it's a Pareto distribution, and we just, for sake of argument, said 80-20 rule. 80% of users want the top 20%, 20% of users want the bottom 80%. And then we thought, okay, well, that's, you're leaking relatively small amount. You are leaking that important bit of information that you want the uncommon stuff. But now most of it's uncommon stuff, so narrowing it down to which uncommon stuff is still very hard. I mean, it's impossible to actually narrow it down further based on the PIR. But yeah, that's when you start doing things like that, the privacy guarantees go from very clear cut, you reveal nothing but you're doing a query, to very nuanced and intricate and hard to actually reason about. So I don't know whether that answers or evades your question, but that's, yes?
Yeah, I didn't quite catch the math that you did a little bit before this. You multiplied a row by a matrix and you got a column. Is that what you had, or?
Just for space, I transposed to get a column. So you multiply a row by it and you get a row, but I transposed it so it would fit on the slide.
I see, okay.
So it's I think you're referring to, okay, right here.
Yes,
Yeah, so you're taking a row matrix that has the same length as the height of the database. You multiply by a database. You get a row matrix, but I wrote the transpose just because otherwise it wouldn't have fit.
Okay.
So, yeah.
Thanks.
Any other questions?
So one question, typically as many of the practical studies started to look at PIR, they found that the key problem is not the communication, but rather computation, which is basically you have to touch each of the element
Yes.
in your thing. So can something happen there? I mean, even now when you are reducing the effort, you're reducing the effort by factor U, but if you count all the servers, it's still RS divided by U and actually multiply with the L. So in that sense, it's maybe more than RS.
It is more than RS. Yeah, it definitely is.
So, I mean, can we...
It has to be more than RS because L has to be bigger than U.
Yeah, but my
is
question
U
was
plus
that
T,
it seems like this computation, I mean, there are interesting studies when you have a really fast network, maybe that's where the trivial PIRs started to do better because these computations are huge. So
That's
any
true.
hope there? Or?
The saving grace is that we're already inherently distributing that computation over several nodes. And the computation that each node has to do is embarrassingly parallelizable. So you can parallelize it basically, not infinitely, but you can parallelize it until each node or each core does like one multiplication, and there's no synchronization issues. You just multiply one thing and then you add the things, and you don't have to synchronize, you just have to collect the results and add them together. So that the parallelization is very easy, but you're absolutely right that it's still, at the end of the day, a lot of computation that has to happen. So that's part of the reason why it's interesting to be able to shrink it by a factor U. We have been looking, just in the past couple of weeks, my student and I started looking at what happens when so there was a little bit of background. There was a paper in 2014 that showed that under ridiculous trade-offs, but still very interesting, you can do PIR where at the end of the day you download one extra bit of data compared to a non-private query. Only one bit, exactly one bit, and it was like a tight, you get this one extra bit. You have to have exponentially many servers, and you have to upload something the size of the database to each server, and there's it's just a crazy, all the other parameters are crazy, but you can download only one bit extra. And so we thought, okay, then they had this impossibility result say if you only want to download one extra bit, you can't do much better than we just did. But if you are willing to download, say, a factor 2 or a factor 4 more bits, then you can reduce all of these parameters quite a bit. And so we thought, well, what if we use the U and Q here to recreate this? So we take our rows that are each this long and we chop them down into really short rows and split them over a whole bunch of rows. And then we use the U to shrink that database down. And we say, rather than trying to fit this all into the L servers we already have, we just say, well, there's more servers now, right? These other protocols are saying the number of servers has to be linear in the size of the data. So what if we say something similar and we say, we're going to make these parameters really big and we're going to just add more servers so we can still answer a query. And you get some really interesting asymptotic. So if one thing, we can do PIR where you download exactly twice the size of a record. And unlike the other protocols where no two servers can collude and nobody can know which subset of servers you queried, here you have an honest majority assumption instead. The cost per node becomes like logarithmic multiplications instead of linear. But if you add up all what every node is doing, it's still more than R times S. And that just seems to be inherent unless you change the threat model. Like if you change the goal of the PIR to get, there's an impossibility result you're coming up against. And unless you change the definitions, you really can't get around that result.
Well, I'd like to thank Ryan. And next week is spring break, so we will see you all in 2 weeks.